Hello and good day. My name is Robert Klar. I'm from Southwest Research Institute, and I'd like to talk to you today about establishing a software-in-the-loop testing environment for spacecraft flight software. Well, first of all, I'll give you an overview of the talk. I'd like to talk about why we're doing this, talk about some of the different testing approaches that are used for spacecraft flight software, and then I go into detail on the software in the loop testing that we're looking into. And I'll talk about some of the tools that we're using, including GitLab, tsim3, and the Renode. And then I'll talk about some of our future work and conclusions. One of the important concepts that's come to the forefront recently has been the idea of a digital twin. Some of the systems that we build, in particular spacecraft systems, are complex, and they require a lot of external test equipment to test adequately. So an alternative that's been proposed has been to represent that physical system with a digital representation. This is a very attractive idea in that it speeds up the development time that it takes and allows us to do testing where otherwise it may not be possible. So one of the reasons that we're doing this is the current development approaches are very time consuming. We want to substantially reduce that time to develop flight software, and we want to be able to provide a meaningful demonstration of system capabilities with digital model. Since available engineering and flight hardware is limited, that can also be a factor in testing. So having a digital model is an enabler for that activity, where multiple copies of the digital model could be used to test various aspects of the flight software in parallel. A third benefit of this type of environment is for long-term maintenance. Long-term maintenance for spacecraft missions can be quite expensive. Missions can last for many years, much longer than their original design life. And by virtualizing that environment, it provides a support environment that could endure longer with less cost to maintain. Why are we doing this? Well, here's some examples of some small satellites, and we want to be able to efficiently build multiple at the same time. One approach that's used associated with model-based design, and it's often used for the GNC system and other control systems in the spacecraft, is model-in-the-loop testing. This type of testing, it works well, and it doesn't involve necessarily you having the full flight software built, just the model of what the flight software is supposed to do. This is a good first step, but it's not testing the flight software that will be put on the actual spacecraft. So it's not a final test. It's just a good early test. A lot of times for control systems, the next step is to go into hardware in the loop testing, where we actually procure articles and run the software on representative hardware. That can be time consuming, and there may be a build-up process to get to where we want to be for testing. So there's two other types of software testing. There's software unit testing, and there has been recently, there's been a lot of work done on unit testing frameworks, and they've become ubiquitous. They are excellent for testing the flow of control and the correctness of implementation of the software. They aren't so good if there's a design bug in the software itself, and they don't do well where hardware is providing a lot of the functions that the software interacts with. One of the newer approaches is software in the loop testing, and what that's really become possible with the virtualization technology that we have today. We use this virtualization technology to run the flight software on a virtual machine to be able to verify the functions that it performs component by component. Here's an example picture, and for software in the loop testing, it really can be viewed, I think, in two stages. One approach to be able to do this software in the loop testing early is to focus on the application software. If your software is structured in a layered fashion, then you can provide spacecraft simulation information directly into the application software. A good architecture for this is one that has a message passing middleware. One example of that is the software bus for the NASA CFE CFS software. And another good example is a system like the robot operating system, ROS, which is a middleware which is used in robotic applications. But both of those things provide a good message passing layer where data can be fed in to the applications. With this structure, then you can abstract away from the hardware and the operating system a bit and work and concentrate on the higher level applications. As the design matures, then you can focus on the lower level software also. Here's where you're getting closer to having real hardware in the loop. And one way to do that is to virtualize the hardware and then feed information through the virtual hardware so that you can run the full flight software stack on top of the virtualized hardware. This allows you to verify your low-level interface software, which you weren't able to verify before. As far as our tool chain, we use fairly standard tools for compilation and static analysis, often a version of GCC or G++. For static analysis, we use Clang Static, and we've also used several of the commercial products for static analysis. For unit testing, for C coding, there is a good set of tools at www.throwtheswitch.org, Seedling, Unity, and CMOC. And we've found these tools easy to use and easy to integrate into our development environment. For C++, one recommendation is Catch 2. This is a tool that has better support for C++ if your application software is developed in that. I'm very much in favor of a continuous integration, continuous deployment approach. And one of the Git front ends, GitLab, has good support for this. What we're going to talk about today are some of the tools that we use for software in the loop simulation. One of them is the front grade Geisler TSIM3. This is a commercial product, and the other is an open source product, which is Ant Micro's Renode. First of all, for GitLab, the continuous integration and continuous deployment tool, they have a very simple YAML textual language that you can use to define the steps that you use in your processing pipeline. And this links up with Git, your Git repository, so that activities can be triggered by events in the configuration management process. They can be triggered by a commit, a merge, or a tag, for example. And there are free and paid versions of GitLab. The free version does support CI/CD options, but there are also some advanced features in the paid versions. TSIM3, this is a commercial simulator. My colleague Emilio Baglioro is going to walk us through that a bit here.
So I'll be doing a quick demonstration of TSIM and how we have used TSIM in the past. TSIM is a very powerful tool created by Front Grade Geisler that we have used on our previous projects that allow us to test our software when hardware is not readily available to us. I'll also be showing some of its similarities to GRMON, another tool created by Frontgrade Geisler. So TSIM allows emulation of several processors, which include the GR712 and the UT700, both of which we have used on previous projects. Using specific switches when starting TSIM, you can also fine-tune some settings such as memory sizes or configurations, or even the number of CPUs to enable. This will allow you to replicate your hardware as close as possible. So first, we're going to start TSIM. And here I have a bash script that has some of the TSIM switches already configured. And now I'm going to load a pre-built VxWorks image along with some bootloader software. We can use the mem command to peek at memory and verify we've loaded code in the correct locations. There are also many other commands available to us that are useful for debugging. Infosys provides us with information about available devices in the system. InfoReg can provide us with register values of a specific device. And so going back to the code I loaded previously, if we use the command boot 0, it will allow us to perform a cold boot. And as you can see, the bootloader has loaded the image, and now the VxWorks banner is being displayed. We can also see that we're in the VxWorks shell. TSIM is great because we could quickly test our image builds, see how our software might interact with devices on our hardware. If I Control C here, we'll break out of the image and have access to the TSIM commands again. Another useful command is BP, and this allows us to set breakpoints within certain sections of the code. We can also use step to step through lines of the code. So not only does TSIM provide hardware emulation, but it's also valuable in that its commands are identical to what is used in GRMON. GRMON is another tool created by Frontgrade Geisler that we use to debug and test software on our development boards. So here, I'm going to start GRMON and connect using FTDI, and I'll also forward the URL. And now I'm going to load a pre-built image that does not require a bootloader. I'll also use the same load command we used in TSIM. And as you can see, it's taking a bit longer to load the image, since we're loading code into actual hardware this time. And now that the image is loaded, you can see output similar to what we saw in TSIM. And if I hit Control C here, we'll break out of the image in a similar fashion as to what happened earlier. And we also have access to several commands that we're familiar with. So I can also inspect the memory location where I loaded my image earlier. We also have access to BP, infosys, and the info-reg commands. All in all, TSIM is an extremely valuable tool that allows us to develop and test code on an emulated system while hardware is being concurrently developed.
One of the strengths of TSIM is that it has a command set very similar to grmon and could be used to develop low-level code such as the bootstrap. Another tool that is an emulator that's open source is a product called Renode. It's got a little bit different focus, so it has a lot of support for maker boards and for boards that have some small integrated peripheral systems on a chip. Structured to have really 3 layers. It has models for integrated chips. It has models beyond that for devices, which may include the chip. And then it can also be used to do larger simulations where you have, say, several wireless devices communicating with each other. Renode also has good test support. It integrates with a Python framework called the Robot Framework. And this is designed to automate a good portion of the testing. On the right side of this slide, I'm showing a bit of the way a CPU is defined here. This is showing the basics for the Leon 3 processor, which we use as in place of the problem processors for this environment. Next, I have a video here. Again, my colleague is going to talk a bit about Renode and show Renode in use.
So now I'll be doing a quick demonstration of Renode. Renode is a development framework similar to TSIM that allows for hardware emulation. It's open source and supports a wide variety of boards such as the Raspberry Pi and the STM32. It even supports several Leon processors. Renode doesn't have the same type of commands like TSIM, where we can inspect memory or set breakpoints easily. However, it does have the ability to connect to GDB. So now I'll start by using the include command for the board I want to use. This will initialize the peripherals on the device I want to emulate. And now you can see the simulated UART in this window that just opened. Next, I'll use the load elf command to load my binary. And lastly, I'll use the start command to start execution of my image. And as you can see in this window, we're able to see the hello world output of the Zephyr RTOS image. Like we did in our previous demonstration, I'll now load the same image onto actual hardware using grmon. And here we can see the hello world output we saw previously in Renode. Renode is a great alternative to TSIM and has the benefit of being open source. It also allows for a great range of customizability, provides the user the ability to create their own custom peripherals to simulate.
So I have a summary chart that shows some of the main differences between Renode and TSIM 3. TSIM3 is certainly convenient for low-level debugging, and it has very good support. It's tailored for the front-grade Geisler Spark architecture processor. So if you're using one of these processors, then I would recommend it. The GR740, the GR712, and the UT700, they do have versions of the simulator that support those processors. Renode supports multiple architectures. It's much broader in the scope of what it can support. It has good support for ARM, and it has some support for PowerPC, and also in this case that we were using it with the Spark. It's an open source solution that is attractive in that you don't have the licensing fees to pay to go with it. And it's designed for the emulation mostly of IoT devices, although it can be used, as we've shown here, to emulate devices other than those just specifically for IoT. It has a simple text-based language for its setup. So as I showed in the earlier slide, the file for creating a processor is not very long or complicated. TSIM, on the other hand, is set up. It uses Tickle scripting. So for those of us that are familiar with Tickle, it has good support for that. It also has a C library that can be used to control it. And it also has very good support, especially now with the newer versions of GRMON. We were showing GRMON 2, but with GRMON 3, they have good support for the GNU debugger. So you can do source level debugging through TSIM. Renode is extensible, and that's one of its more attractive features. It allows you to create very simple peripherals in Python, and you can create more complex ones using the C# language. The TSIM 3 simulators are mostly just designed for use out of the box, and they do have some good support for the peripherals that are included on the processors that it supports. As far as future work and conclusions based on this, the extensibility of Renode has proven to be very attractive to us, and we're looking at modeling more of the peripherals for some of our standard FPGA IP cores using the tool. The goal is to create a corresponding simulation for each of our standard IP cores. There's also some tools that may help in the conversion process. There's a tool called Verilator, which takes Verilog code and can output code in various languages, software languages. So this is something that has been supported by Ant Micro and other companies. And we were looking at to see what capabilities there are for converting the IP cores that we have. For the front grade Geisler processors, I would recommend the TSIM3 product. It does get you started quickly. And for the processors, if you are using one of these processors, they're very easy to use. I've included some URLs here for some of the more detailed documentation for these products, and I've listed them here with each of them. And that brings us to the end of the presentation. Again, thank you for your time today. If you do have any questions on what we've discussed here in this presentation, please feel free to email myself or Emilio. Our emails are on the very front page of this presentation.